Hi class, welcome to lesson 5 of unit 1. Today we are going to convert between Celsius and Kelvin temperature scales and evaluate accuracy by calculating percent error, something that we looked at briefly in last lesson. Temperature is defined as the measure of the average kinetic energy of particles in a substance. Kinetic energy is the energy due to motion. So the higher the temperature, the faster the particles are moving. Temperature does not depend on the amount of matter you have. You can have a cup of boiling water and a pot of boiling water, and they will have the exact same temperature. Although you are probably most familiar with the Fahrenheit temperature scale, which we use to describe daily temperatures here in the United States, in science we are going to use the Celsius and Kelvin scales. The thermometers in lab are Celsius thermometers. Two important points on the Celsius thermometer that you need to know are 0 degrees Celsius, where water freezes, and 100 degrees Celsius, where water boils. Now, at a temperature of negative 273 degrees Celsius, there is no kinetic motion of particles. This temperature is called absolute zero on the Kelvin scale. The Kelvin scale is used so that 0 degrees corresponds with 0 molecular motion. In the Kelvin scale, water freezes at 273 degrees Celsius and water boils at 373 degrees Celsius. Notice that there is 100 degrees difference between the freezing temperature of water and the boiling temperature of water in both the Celsius and Kelvin thermometers. You can find the equation to convert between Kelvin and Celsius temperatures on the back of your reference table on table T. As I'm sure you know, as you change the temperature of a substance, you can alter its state of matter. So, at room temperature, water is a liquid. If we decrease the temperature enough, and we take it to 0 degrees Celsius, we can freeze water. Or if we raise the temperature enough to 100 degrees Celsius, we can boil the water and turn it to a gas. It is important that you are able to determine which state of matter substances exist at different temperatures. One of the most common temperatures that we will examine in chemistry is at standard temperature and pressure. This temperature is defined on reference table A. To determine the state of matter of any given substance at a given temperature, you simply have to make a number line evaluating its melting point and boiling point and see where the desired temperature falls. If your given temperature falls before the melting point, your object will be a solid, as it hasn't melted yet. If the desired temperature is after the melting point, but before the boiling point, your substance will be a liquid, and it is melted, but it is not boiled. If the desired temperature is after the boiling point, then your substance is a gas. It is both melted and boiled. Let me show you how we can determine the state of matter of various elements at STP. STP is found on reference table A and is defined as either 0 degrees Celsius or 200 degrees Kelvin. When using the data on reference table S, we're going to choose the Kelvin number 273. So let's look at fluorine. Fluorine has the melting point of 53 degrees and the boiling point of 85. So this number 273 in a number line would fall after 85. Notice that a number line would read 53, 85, then 273. Since the STP value falls after the boiling point, fluorine is a gas at STP. So notice I've written its chemical formula with a subscripted 2 because fluorine is diatomic, and I've added a subscript of G to indicate that it is a gas. Now we can move on to bromine, element number 35. So when we repeat the same step, again we're using STP, which is 273 Kelvin. We must use Kelvin because this data table, this data is in Kelvin, and we try and put in a number line for bromine. What we'll see is that 273 falls between its melting and boiling point.
So bromine is a liquid at STP.
For iodine, you're going to have to refer to the second part of reference table S. And we're still going to insert 273, which is the same as STP, into our number line. 273 falls before the melting point. So that means iodine is a solid. Again, just refer to where your desired value falls in a number line. If it falls before the melting point, you have a solid. If it's between melting and boiling, you have a liquid. And if it follows boiling, you have a gas. This number line technique works at any given temperature. So here in the next example, we're examining elements at a temperature of 35 degrees Celsius. Now we can't use the number 35 directly into the data table because the table gives temperature in Kelvin. But if we convert 35 Celsius to Kelvin temperature, or 308 Kelvin, then we can make a number line. So when we look at sodium, element number 11, the value of 308 falls before its melting point. So sodium is a solid at 308 Kelvin. One more example we'll use is for argon. Argon is element number 18. When we insert the number 308 into argon, we find that it falls after both the boiling point and the melting point. So 308 falls here. So argon is a gas at 308. Now it's your turn to try to determine the state of matter that gallium is at 308 Kelvin. Then find the state of matter the following elements are at STP. Finally, we'll examine the percent error calculation one more time. Percent error formula is found on reference table T, or the back of your reference table. Here we must have a measured value. Measured values are always going to be found in lab. The accepted value are going to be values that are given as an accepted value or found in reference table T. Information, particularly reference table S. Now recall that your percent error could be positive or negative. A positive percent error means the measured value is greater than the accepted value. A negative percent error means the measured value is less than the accepted value. That concludes Lesson 5 for Unit 1. See you in class.